Well, now today I will talk about the concept of entropy and how it is related to the second law of thermodynamics. Um, just remember that the second law of thermodynamics or entropy uh, is inherently related to the first law, and the first law gives rises to the conception or the concept of entropy. Okay, it is the foundation or the genesis of the concept of entropy. Let's see how it is. Before I move on, I just tell what is entropy in a qualitative term. So, few points I'm just write down. Please note this. One, entropy is a measure of randomness. So, entropy is a measure of randomness. What do I mean by that? See, by definition, when the process is, more unorganized, or there are more freedom for, for example, a gases in a chamber. If the gases have more freedom to move around, or let's say more freedom to, go anywhere else, or let's say you have a lot of space and very small amount of occupants in the system, so the randomness is more. I will talk about some configurational entropy, the concept of entropy, in some other context. But for example, so here the concept is that it's a measure of randomness. Okay. So if a process is spontaneous, that also means that the final state will be more random than the initial one. And in essence of being a process to be random is that the process will have a lesser amount of energy than the initial state. So the final state will have lesser energy from the initial state. For example, you have a compressed volume of gas. Okay, so if this volume is V1 and if this is the pressure you are exerting P1, so if you just release the pressure to an extent, this is P2 and the volume becomes V2, where V2 is greater than V1 and P1 is less than P2, or P1 is greater than P2. So what happens in this process is that you increase the volume of the system, so you increase the randomness of the molecules. So molecules have more space, more freedom to move around. So by decreasing the pressure, you actually decrease the total energy of the system by increasing the entropy as well. So we'll see how entropy affects the total energy of the system when we talk about Gibbs free energy and how it is dependent on temperature. The next point is that the second law of thermodynamics is basically or let's say del S is del Q reversible by T. So it is the first definition of entropy. The third definition of entropy, please note this. This is one of the important formula. I will discuss in details, but still, this is the first definition of entropy. And it's also the second law of thermodynamics. Del S is del Q reversible by T, and also del S is integration Cp by T dt. Okay. So please keep this formula handy. So whenever you will be doing any calculation for entropy, will always either will proceed by this one or by this one. I have already talked about the concept of constant heat capacity. It might be Cv as well. We'll see when it will be Cv and when it will be Cp. So these are the standard formula. What does this mean? I'll just briefly tell you. Remember the first law of thermodynamics. d is equal to del q minus del d. I will keep repeating this first law of thermodynamics because whatever calculation you do, whenever you do a calculation, always remember it always follows this first law of thermodynamics. It is always derived through the first law of thermodynamics. Remember, I talked about that del Q is not a directly measurable quantity, and we need to substitute with some measurable quantity in terms of P, V, and T, because that's what we measure in real life. So just see that this entropy is another substitution for calculation of total Q. But to be very frank, this del Q is calculated or can be calculated in a process where there is a state change or there is a change in the state of the material. I will talk about that, and from there we can calculate del S directly. Otherwise, I will talk about the Cp by Tt dt concept. So these are the most important. Just note it as the entropy formulas 1 and 2. Very, very important. We'll solve numerous problems with this entropy concept. Now let's get the other aspect. Okay, so what is what? So now I'll just broadly classify. See, as a thermodynamic system, I won't go into the details. You can refer any standard books to get the concepts or the theories of entropy, how it is defined, how it has been derived from heat and work. But I will give you the essence of what all those means. See, any process in thermodynamics either classified as a reversible process or a reversible process. By definition, an irreversible process is extremely fast, extremely spontaneous, and once you reach 1 to 2, you need to spend a very, very high amount of energy to come back to 1. So this is a reversible process, which is a spontaneous process, very fast process. Sometimes it is not fast. For example, sometimes we talk about corrosion. But in chemical reaction that you normally see, vigorous reaction rates, these are all spontaneous process. And very high amount of almost impossible to get back energy must be expended to get back to state 1. So that is an irreversible process. What is a reversible process? Reversible process is just like a piston. You apply the pressure P1, you get a volume V1. You just slightly decrease the pressure into system, you get a P2 and you have an increased volume V2. So this is a reversible process. You can easily switch back and forth. You can easily switch between two states. That's your reversible process. Thermodynamics, all the calculation always talk about reversible process. There is no way you can calculate the energy change or anything else for an irreversible process. So we'll always talk about equilibrium and reversible process in thermodynamics. Now another concept. Always remember that in thermodynamics, I should have told you earlier, you never calculate the absolute value of any quantity or any entity in thermodynamics. You always calculate the change except pressure, volume and temperature. For example, you cannot calculate the absolute enthalpy. You calculate change in enthalpy. You cannot calculate the absolute entropy. You calculate the del S. But entropy has an advantage. I will talk about that. You calculate delta G when we talk about free energy. You calculate change in internal energy del U. You always calculate del Q and so on. So almost all the defined thermodynamic quantities are there. H, S, G, T, U. This is the main thermodynamic quantities. You always calculate the change. You never calculate the absolute value. Now, just erase this one. Once we have understood that, a reversible process. So again I will write, reversible process. It will be like an algorithm. The way I will tell you to calculate entropy, you will never fumble to calculate entropy. You just remember this algorithm, how to approach a problem of entropy, and you will never falter. The first thing that you should choose whether this is a reversible process or it's a irreversible process while calculating entropy, delta S. This is the first thing. Whenever you are given a problem in entropy, just look at the problem and understand if the state change is done reversibly or it is done irreversibly. This is the first thing. So the first step is to determine whether it is a reversible process, irreversible process. Second, if it is a reversible process, then find out is that change in state is occurring at a constant temperature or not. This is the second thing you check. What do you mean by that? Suppose there is a phase change. For example, liquid water, or let's say ice and water. Ice and water equilibrium. Ice and water equilibrium. This equilibrium occurs at 0 degrees centigrade or 273 K. Remember, whenever you are doing calculation in thermodynamics, always choose SI unit, and your calculations should be always done in SI unit, that is in Kelvin. Always remember this. Never use any centigrade thing while calculating. You can convert it into centigrade while reporting your final results, but while in the calculation process, you always use the SI unit, that is Kelvin. So ice water equilibrium, or I can say water vapor equilibrium. Okay, so this process, or the equilibrium of this process, or change in ice to water, occurs at the same temperature. When we say this is a phase change. So first step is determine if it's a reversible process or irreversible process. Then break it up whether it's occurring at a constant temperature or it is not being done at a constant temperature. If it is a constant temperature, your third point will be, if you are now asked, then what is the change in entropy for this process? The change in entropy will be calculated as follows. Reversible heat, that is the latent heat. Okay, the latent heat divided by the temperature at which the equilibrium is occurring or the phase change is occurring. It's a constant temperature. This is Tc, means it's a constant temperature. For example, if I need to calculate for this one, you just divide the latent heat for transformation from ice to water multiplied by number of moles. For example, let's say 10 grams of ice has been converted to water. So what is the change in entropy? If you are asked to do that, you just convert the 10 grams into number of moles multiplied by the, so it will basically N into latent heat. I just write LP per mole multiplied by Tc. So this is the straight. I will just give you some examples how to calculate. The examples will be there. So N into LP by Tc. So this is how you calculate the change in entropy for a phase change that is occurring at a constant temperature for a reversible process. Right? Understood? So one part is your complete. The next part, the next calculation. What if this reversible, okay, so we have determined that it's a reversible process, but let's say you're increasing the temperature of a system. Suppose there is a body A and you are increasing the temperature from T1 to T2. Yes, always remember, as temperature changes, the randomness of the system changes because there is normally a volume expansion. So more volume, same mass. So you have more freedom to move around. So you increase the randomness of a system. So your entropy always increases for materials from going from lower to higher temperature. So at higher temperature, your entropy increases. Now how to calculate that? Because it's the same state, there is no change in state. And only your temperature is being increased from T1 to T2. For these processes, where there is a change in temperature, but state is same, okay, we'll again write this formula only, del Q, or let's say I will put it in a delta form, nothing matters, ds equal to del Q by dt. Okay. So now the third question, is this change is being done at a constant pressure or at a constant volume? By default, if nothing is mentioned, so it is assumed that everything, the system is being, operated at a constant pressure. So if it is a constant pressure, so remember, so this is a constant pressure. The moment you write this at a constant pressure, now again come back to the formula, the original formula. Sorry, is del Q by T, let's say. Del Q by T. This is a variable T. Remember, this T is not constant now. Now I have to substitute for Q, right? So how do you substitute for Q? So del Q, del T, constant pressure is made is Cp, right? Del Q, del T at constant pressure is Cp. So if I substitute this one, so del Q is equal to Cp dt. So I'll write Cp dt by T. Extremely important formula that I have discussed at the first slide while beginning this tutorial. Cp by T dt. So if you want to calculate the change in entropy for a temperature range, how do we do that? You simply need to integrate it. Let's say from state 1 to 2, this ds is Cp by T dt, T1 to T2. Remember that Cp will be given as a function of temperature. So Cp will be expressed as a function of temperature. You have to plug in those Ft by T, T1 by T2 dt. So just do the integration and find the change in entropy. Change in entropy for a reversible process, whereas there is no change in state. So what is the reversible process? No change in state. No change in state. Third one, constant pressure. Right? Understood? So that is going to be your concept. Okay. Now, what happens if it is done at a constant volume? Let's check. So reversible process, then you find out there is no change in state, only the change in temperature is being done. So the system remains at the same state. If it is solid, the temperature is increasing. Then you find out it's a constant pressure or a constant volume. If nothing is mentioned, then it's a constant pressure. Now see, if it is specifically mentioned that it's not a constant pressure but a constant volume process, how we do that? Again, I will go back to the first law of thermodynamics. du is equal to del Q minus del W, right? So for a constant volume process, P del V is 0, no change in volume, only your pressure is variable, so your del W is 0, no useful work done. So du is dq. Now remember how we defined Cv, if you remember it, del Q del T at constant volume is equal to del U del T is your CV, right? So similarly, ds will be simply CV by T dt T1 to T2, right? CV by T dt. So constant, if it is a constant volume process, it is specifically mentioned. So CV will be given. CV will be given as a function of temperature, or otherwise it might be also a constant. So just check for it. The question will provide you whether this is a function of temperature or it's simply a constant. Plug those values, do the integration, and find the change. Again, it's for a change in temperature for a reversible process. Okay. So this is, now broadly we have done the reversible process. So reversible process. So just if I write state change summary, del S is latent heat Q reversible by temperature, constant temperature. See, now if there is a temperature change, then again constant pressure, constant volume. If it is a constant pressure, Cp by T dt. If it is a constant volume, Cp by T dt. We're done with all the formula for calculating entropy. So this is it. If it is a state change, just plug this value. You will be provided the heat of fusion or heat of melting, the latent heat basically, multiplied by the number of moles if it is given in the molar form, or if it is given the total energy is given. So just divide the total energy by temperature, always in Kelvin, never degree centigrade. Then if this is not the case, so come back to a temperature change. So there will no change in state, only the change in temperature. Then find out whether constant pressure or constant volume. If constant pressure process, Cp will be given. If constant volume process, Cv will be given. Accordingly, you do your calculations. Okay. Now, for example, how do you I will just go to reversible process. Then I will talk about that. Now the most difficult part, and the questions are normally asked from this part, because everyone knows that from calculation of entropy for a reversible process is pretty straightforward. You just do the integration or division to get your results. What about an irreversible part? This is very tricky as well. Okay. So let's see irreversible. What we mean by irreversibility. See, I will just give you two cheat sheets kind of thing. Okay. The first thing is, if you are dealing with a reversible process, so either it will be mentioned as undercooling or supercooling. Normally this is given as undercooling or supercooling. The moment you see undercooling and supercooling thing, it should strike your mind straight away that this is a reversible process. Why this is so, we'll talk about that. This diagram you should know by heart for a calculation of irreversible process, and you need to find an entropy. This is the diagram you should draw always. There is no way you can skip this diagram and find out how to calculate entropy. Another important thing is I should have mentioned it also. Entropy is a state function. We will see how this important concept of state function comes into play here. Now, please spend some time. You can also pause the video or make it slower, or note every point I am telling, because this is the most important question normally asked in gate metallurgy For irreversible process, find the entropy. People, sometimes students even don't understand what is the process and which part is reversible, which is reversible. Why not? Why yes? So this part I'm explaining. Please be very careful. It is one of the most important topic of calculation of entropy. Right? Well, set to go. Now we'll start. I think everything is visible over here. Suppose A is a material and exists in liquid and solid form. So there is obviously a temperature of melting. So if T is greater than Tm, if temperature at which the material is existing is greater than temperature of melting of the material, then the state will be liquid. If T is less than Tm, the state will be solid. Right? If T is greater than Tm, the material will be in liquid form. If T is less than Tm, it will be in solid. Now, what is undercooling and supercooling? Undercooling is a process by which you extract the heat out of the system and still you are keeping it in a liquid form. Understand? You are taking heat out of the system. T is less than Tm. So by default, a liquid will transform into solid the moment you go below the melting temperature. So liquid will transform to solid spontaneously, but you are not allowing that. You're not allowing that. You are still keeping, by some method, you can do a Google search how to do a supercooling or how to do undercooling. That is not our concern here. The real thing is how the processing is. So you are still, undercooling is this process where below the melting point also A will still remain in the liquid form, where that is, it violates the spontaneity of the process. Okay, a supercooling is just the opposite thing. Even you increase the temperature beyond the melting point, the solid still remains as solid. So this is case of supercooling or undercooling. You can also say supercooling. Or it's sometimes says superheating. So undercooling or superheating or supercooling, these are the normally processes that violates the basic nature of phase transformation. So undercooling, you cool it below the melting point, that the material still remains in the liquid state only. It doesn't transform into a solid state. So this part now see, this is the melting temperature of a liquid. You're extracting the heat, that is Tm minus delta M. Delta M amount of decrease in temperature occurs, but it still stays in the liquid form. Okay, and here you just see this is the most spontaneous process. You add amount of heat and it transforms to solid Tm. That is a phase transformation. Okay, no phase transformation, temperature change. It's the same as no phase transformation. It's the same as this one. So in this process, a liquid transforms to a liquid at a temperature which is below the melting point. Here it is a state change at the constant temperature. Here the temperature is Tm and it's also in Tm. There's only a change of state, liquid to solid. So it's a phase transformation. Now here the temperature, or from here to here, a solid transforms to a solid at a change in temperature. So from T minus delta T, so Tm, so it's just a change of temperature. There is no state change. Look at this process here. This is of the concern. This is the real thing that we are talking about. This one, if we talk about 1, this is 2, this is 3, and this is 4, we'll not talk about 1, 2, 3, 4. Let's say 1, 2, 3, 4. 1, 2, 3, and 4. Now, if I talk about 2 to 3, this is the process. See, here the liquid is being transformed into solid. Okay? And Tm minus delta m at a temperature where it should not exist as liquid at all. So this part we call it an irreversible process because you don't know the Cp of a liquid below Tm minus delta m, how it should behave. Okay? Or rather I would say this is an irreversible part, irreversible transformation. Okay, this is the irreversible. All this 1 to 2, 1 to 2, 1 to 4 and 3 to 4 are reversible process, and here the formula that will be used, there is a Tm to Tm minus del m Cp. See, it's a liquid, right? Cp liquid by T dt. Okay, for this process it will be del Q reversible by temperature Tc, or here the temperature is Tm. For this process it will be Tm minus del m to Tm Cp solid by T dt. What about this? So we can calculate directly, right? So for this process the entropy change is Tm melting point, it goes to a point where it is below the melting point Tm minus delta m. I'll just write it down in a clarified way, otherwise it's being too congested. It's very important, otherwise the calculations are very straightforward. Again, let me draw the cycle on. This is Tm, this is Tm minus del m, Tm minus del m, Tm. This is a solid, this is a liquid, this is liquid, this is solid. This is the irreversible part. And we have no formula to calculate the entropy change in a reversible part. These are all reversible part. So 1, 2, 3, 4. 1 to 2 integration Cp liquid by T dt, temperature of melting to temperature below. So this is the delta S, 1 to 2. Okay. So for this one, liquid to solid transformation, this is a phase transformation. So del S 1 to 4 or vice versa is equal to del Q reversible by Tm. Okay. For this process, Cp solid by T dt. Just be careful. Cp liquid is different from Cp solid. It will be provided. Temperature of melting minus del m to Tm dt, right? And for here, I don't know any formula to calculate this. So how will you tackle? If you are asked, you will be always asked that only, 2 to 3. So this is the big concern. How do you do that? What is about del S 2 to 3? See, remember I told you that entropy is a state function, right? So for any state function, okay, so for any state function, it doesn't matter which path it has taken. Only matters which is the final state, that is the temperature, the final temperature it has reached. So for this system, okay, for this system, if I need to calculate del 2 to 3, can I just say that del 2 to 3, delta S 2 to 3 is same as delta S 2 to 1 plus del S 1 to 4 del S 4 to 3. So it's summation of this one, and this one. Summation of this one, and this one. if you just add this process entropy of this entire process, so we'll reach here. That is to say, it's same to go from 2 to 3 via 2 to 1, 1 to 4 and 4 to 3. Why I have taken this process? Because I know how to calculate the change in entropy for a reversible process, but I don't know how to calculate the change in entropy for a irreversible process. So if I just add from 2 to 1, 1 to 4 and 4 to 3, I know how the change in entropy for 2 to 3. Okay? So that is how you calculate. So if I just translate into formula, how will it look? So if I need to calculate del S irreversible, I just put an icon for 2 to 3, the formula will be Tm minus del M to Tm Cp liquid by T dt plus reversible by Tm plus from 4 to 3 Cp solid by T dt Tm to Tm minus Lm. So if I just add these three processes, I will reach 3 from 2 to 3. So that is the quantification for irreversible change in entropy. Always remember that whenever you need to calculate change in entropy for an irreversible process, to draw this cycle, find out which are the reversible process, which data you are known, which data are known to you, then just add the process accordingly. For example, if I need to calculate from 3 to 2, how will I do that? I will go from 3 to 4, 4 to 1, 1 to 2. So this directionality should be maintained, right? That's it. Fine.